Hello students. Now we are going to discuss the next part of the syllabus, that is solution of homogeneous PDE involving derivatives with respect to one independent variable only. So in the previous part we discussed solution of non-homogeneous PDE by direct integration. The next part of the syllabus is solution of homogeneous PDE involving derivatives with respect to one independent variable only. First, when the equation is given, we have to analyze that whether the given PDE is homogeneous or non-homogeneous. If it is homogeneous PDE, so we have to observe the next condition given in the heading is that must contain only one independent variable. That is, suppose that the dependent variable has been differentiated partially with respect to one independent variable, say x only. That is, just I write one example. Dou square u by dou x square plus u equal to 0. So this is the partial differential equation where x is the independent variable and u is the dependent variable. So in this is what we call homogeneous. This is called homogeneous PDE and containing only one independent variable x. So there is another example. For example, dou square u by dou x dou y plus u equal to 0. This is also homogeneous PDE but containing two independent variables. So as by the heading we are discussing, the equation, the homogeneous PDE must contain only one independent variable, so not two independent variables. So this difference you must remember while solving the problem. See that the given equation must be homogeneous, and next the equation must contain only one independent variable. So when this is the condition, then we can apply the procedure. Now what is the procedure? When we confirm that it is a homogeneous, first condition, the next one is it must contain only one independent variable. So as we took this example, that is homogeneous, right, and then containing only one independent variable. So this is the another example containing two independent variables. So to this kind of equation we cannot apply the procedure what we are going to discuss. So only for this we can apply the following procedure. Now the procedure is what? The PDE can be treated as an ordinary differential equation, that is, so here, so this is the homogeneous PDE containing only one independent variable. So this we are going to consider from PDE to ODE. We convert the partial differential equation to ordinary differential equation, that is, this dou square u by dou x square becomes d square u by dx square plus u equal to 0. So now this become ODE. So this ODE we solve. So as we discussed earlier, the method of solving the ordinary differential equation, that is, we convert this in the standard form, that we write d square plus 1. So where capital D is d by dx, so that we write as d square plus taking u common, right, then it becomes d square plus 1 into u equal to 0. and then we write the auxiliary equation, that is m square plus 1 equal to 0. From this we find the roots of the equation, that is m equal to plus or minus I. So these are complex roots. Okay, depending on the nature of the roots we write the complementary function. So this complementary function is the the general solution of the ODE, that is we write as u equal to, that's a complementary function equal to, so as we have the complex roots we write this as a c1 cos, so independent variable is x, so that is c1 cos x plus c2 sin x. So this is the solution of the given equation. And again that one more point we have to remember, so in this we have arbitrary constants c1 and c2. So these arbitrary constants we replace as a arbitrary function of other variable, like as in the previous we discussed, when here as a u is a if u is given in terms of x, so as this example we consider, so it is understood that u is a function of both x and y. So therefore what we do, so these arbitrary constants we replace as a arbitrary function of other variable. The other variable we take as a y, that is f of y into cos x plus, so we take the another notation, that is g of y into sin x. So therefore the solution is given by f of y into cos x plus g of y into sin x. So this is the required general solution of the given PDE, okay, which is homogeneous and containing only one independent variable. Okay, this is the overall procedure. Now we discuss one example with the initial conditions. Okay, so here is one example. The equation is dou square z by dou x square plus z equal to 0. This is what just now we discussed. So here we have a z, right? This is the homogeneous PDE containing only one independent variable, and with this some conditions are given, that is x equal to 0, z equal to e raised to y, and dou z by dou x equal to 1. So these are the conditions we are using to find the values of arbitrary functions which are in the solution, right? So first we confirmed that this is the homogeneous containing only one independent variable, right? Then we write the given PDE to ODE. We write the PDE to ODE, so that dou square z by dou x square becomes d square z by dx square plus z equal to 0. So writing in the standard form, then we write the auxiliary equation. The roots are plus or minus I, which are the complex roots. So then we write the solution as z equal to c1 cos x plus c2 sin x. Now we replace these c1 and c2 arbitrary constants as arbitrary functions of other variable, that is y. Okay, so this is the solution we got. Now the conditions are x equal to 0, z equal to e raised to y, and dou z by dou x equal to 1. So how we consider these as a two conditions? The one is when x equal to 0, z equal to e raised to y. This is the one condition. The second condition is when x equal to 0, dou z by dou x equal to 1. This is the second condition, right? These are the two conditions we have. Now we have the solution z equal to f of y cos x plus g of y into sin x. So in the process we do not have dou z by dou x, so therefore first we use the condition x equal to 0 and z equal to e raised to y in equation 1, So putting z equal to e raised to y, then f of y x equal to 0, that is cos 0 is 1 plus g of y sin 0 is 0. So therefore we got the value of f of y as a e raised to y. So this is the one value of the arbitrary function. Now the second condition is x equal to 0 and dou z by dou x equal to 1. So we need to find dou z by dou x from equation 1. From equation 1 we find the value of dou z by dou x. That is, we differentiate z with respect to x. Dou z by dou x equal to c1 differentiation of f of y here. This f of y cos x is minus sin x plus g of y, then differentiation of sin x is cos x. So in this we substitute the values x equal to 0 and dou z by dou x equal to 1. So here dou z by dou x equal to 1 and sin 0 is 0, this term becomes 0, then cos 0 is 1 into g of y, therefore g of y equal to 1. So now finally we substitute the value of f of y as e raised to y, g of y equal to 1. So in this equation 1. So therefore finally the particular solution is z equal to f of y is e raised to y into cos x plus g of y is 1 right into sin x. So this is the final particular solution of the given PDE. So likewise we can do some other examples. Okay, thank you.